We're looking at question 16, June 2024 paper. In this question, you're given a reaction of the decomposition of hydrogen peroxide. And it's asking you to calculate the free energy, or delta G, in kilojoules per mole. You see, for this reaction, for this question, delta G is equal to delta H minus T delta S. And delta H, we need to work out the enthalpy change of the reaction. And you see, they've given us formation values. So what we do, we need to work out the enthalpy change of the reaction using formation values. So this is your enthalpy change of the reaction, and the formation, the formation will be from its elements in their standard state. So the arrows actually go up. And so the enthalpy change of formation of hydrogen peroxide, H2O2, you're going against the arrow here. You're going against the arrow, so it's going to be minus that. And here, you're going with the arrow, so it'll be plus that. So how do we work out delta H? Delta H would equal minus 188 plus minus 286. And you see the energy change from O2 to O2. Whoops, I missed a, didn't make it diatomic here. The energy change from O2 to O2 will be 0 because there's no chemical change happening. So delta H would equal that's minus 98. We'll come back to that value in a moment. Delta S, which is your entropy change. Entropy change of a reaction is products minus reactants. Always remember that. The entropy of the products minus the entropy of the reactants. So that's going to be products is 110 minus the reactant, which is 70.0 and 205. That gives us oxygen is half a mole. You see this half mole over here? So we need to divide the 205 by 2. So it's going to be (62.5), and you see it's actually I made a bit of a, got these the wrong way around. It appears that it's reactants minus products. Have I got this the wrong way around? Let me just double check something, ladies and gentlemen. Bear with me. Entropy, I'm just looking at the so this is free energy. Yep, here we are. Just looking at the textbook. And I have Oh, it is products minus reactants. Yeah. So what have they done? They have done products minus reactants. Ah, so I'm right, but I wrote the wrong values. That's what's going on here. Yeah, I was right. So, but the products here, ladies and gentlemen, is water, which is 70, and 205/2. That's your products, minus the reactants, which is 110. Got it the wrong way around. Apologies. And this gives us 62.5. The problem is, this is in joules per Kelvin per mole. So we will need to divide this by 1,000. Kilojoules per Kelvin per mole. And what we now do is plug in all these values. So it's going, delta G will be equal to minus 98 minus 25 degrees, convert it into Kelvin. So we add 273, which is going to be multiplied by the entropy change, which is 0.0625. We use double brackets, and that gives us they want it to 3 significant figures, minus 117. They've not asked you this, but is it feasible? Yes, it is feasible, because the answer is negative. Because delta G is less than 0, it makes it feasible. They could ask you this in your exam. Where are the 4 marks from? 1 mark is from 98. 1 mark is for the entropy change, one of these two. 1 mark is using the formula delta G, or this one over here. Yep, and the last mark is from here, the answer. This is an interesting question. The decomposition of hydrogen peroxide is feasible according to the calculations, but suggest why it still does not take place at 25 degrees Celsius, despite being feasible. You see, this type of question comes up often. Sometimes reactions can be feasible, but they are just too slow. That the rate of reaction is too slow. Or you could say that sometimes the activation energy is too high. Usually for the decomposition of hydrogen peroxide, a catalyst is usually used. And why is a catalyst used? It's because what does a catalyst do? Sorry, it lowers the activation energy. So any one of those 2 points. This brings us to the next point about using a catalyst for this reaction. It can be increased the rate by adding a small amount of powdered, which is a solid, magnesium oxide, MnO2. It acts as a catalyst. Complete the enthalpy profile diagram using the formulae for the reactants and products. We know that it is an exothermic reaction because we worked that before over here. It's an exothermic reaction. So your reactants will be here at a higher level, and you've got your products at a lower energy level. So what we've got is hydrogen peroxide here, which is a liquid. You've got water forming, which is a liquid, and half O2, which is a gas. You've got your activation energy, which starts from here. This is your EA. And for your, because you can only use one black color pen in the exam, I'm not going to use colors here, just draw over it. But be very careful and very clear that this smaller arrow represents the activation energy in the presence of a catalyst. It wants you to label delta H as well. So the arrow start on the line and down to the level of the products. Your arrows, the direction of them must be crystal clear. Explain why MnO2 is described as heterogeneous catalyst. You see, hetero means different. They could ask you in the exam, what does homogeneous catalysis mean? Homo is same, hetero is different. This is where the catalyst, or MnO2, is in a different phase or physical state to the reactants. In this case, which is a liquid. MnO2 was a solid, and the reactant is a liquid. Next question. It says 2 oxidation states of Mn3O4 of manganese in Mn3O4 has 2 oxidation states. Identify them. This is -2, -2, -2, -2. Manganese, we play around with numbers. It can be, so this needs to add up to a total of +8. And you got 3 manganese. So we could have a +1, +1, and a +6. Or we could have a +2, a +3, +3, and a +2. Any one of those combinations gets you the mark. Next question is about lattice enthalpy determination by using all these values: atomization, ionization, first and second, electron affinity, first and second. And you've got your formation as well. So all these values here are given. Define the term lattice enthalpy. Lattice enthalpy, in this case, we've got MnO. Lattice enthalpy is where 1 mole of an ionic compound, 1 mole of an ionic compound is formed from its gaseous ions. And putting that into words. Write this down. This comes up often. 1 mole of an ionic lattice is formed from its gaseous ions. Complete the diagram, adding the species present on the dotted lines. Include state symbols. We see the bottom one. Let's start from the bottom. This is an easy one. It's going to be the manganese oxide, manganese 2 oxide solid. That's the ionic compound that's formed. If you look, you're playing a game of spot the difference. You see for this one over here, what's going to happen is before manganese turns into a +1 ion, it needs to be atomized where it's turned into a gas. And that's what you would have. Then, if you look at this one over here, this is going to be the second ionization energy. Sorry, the second bear with me. If you're gaining, yep. Look, this is the first electron affinity. This is the first electron affinity, where Mn2+, that stays the same. Oxygen has now gained 1 electron, and there's still 1 electron left. That's what it would be. Mind you, with these enthalpy profile diagrams, the second electron affinity is always endothermic, because if you're trying to combine 2 negatively charged particles, you need to overcome that repulsion because it's the same charge. That's why it's an endothermic reaction. So these are your missing species. It says calculate the lattice enthalpy. There's a hack for this, which has never let me down. That hack is enthalpy change. The lattice enthalpy is equal to the enthalpy change of formation minus everything else. So using my calculator, where's the enthalpy change of formation? Is over here. Let's do this. And let's just double check that there's no big numbers anywhere. Atomization is where 1 mole of gaseous atoms are formed from its element. So we don't need to worry about the half. So what we do, minus 385 minus 798 minus 141 minus 1509 minus 717 minus 249 minus 281. With my calculator, I've got minus 3798, which is correct. That's the end of that question. See you tomorrow.